So in this video we want to look at a related rates problem involving an angle of elevation. So the example says a camera is mounted on the ground a distance of 1,000 feet from a rocket launch pad. If the camera tracks a rocket that is launched from the pad, find the average rate of change of the camera's angle of elevation 10 seconds after the launch, assuming that the vertical position equation for the rocket is height as a function of time equals 40t squared, where height is being measured in feet and time is being measured in seconds. So if we just draw a picture of the scenario, we have a launch pad, and from that launch pad a rocket is going to be launched vertically upwards. So at any point in time it's going to be at this position. The height of the rocket is modeled by the equation 40t squared, so this height is changing. And over here off to the left, possibly, is a camera that's mounted, and the camera is going to have an angle of elevation relative to the rocket as it pivots upwards to keep the rocket in frame while it's taking the footage of it. And the distance from the camera to the launch pad, we're given that that's 1,000 feet. So we have a constant horizontal distance, but a changing vertical distance and an angle theta of elevation. And we want to know how fast that angle is changing. So we're interested in time equal to 10 seconds. At the 10-second mark, we can actually calculate the height at which the rocket would be. So the height, when we plug 10 into the height model, we get 40 times 10 squared, which is 4,000. So we know at the 10-second mark that this is going to be 4,000 feet. We also know we can then calculate the distance from the camera to the rocket at the 10-second mark. We know that this distance is just going to be given by the Pythagorean theorem as the sum of the squares of the legs of the right triangle. We're assuming that this is perpendicular here. So the distance between the camera and the rocket at the 10-second mark is going to be 1,000 squared plus 4,000 squared. And we can fuss with that later. And then we want to know the rate of change of this angle. So we need a function that includes the angle and the sides of the triangle. So what we want to recognize is that the tangent of the angle we're working with is going to be, from trigonometry, the side opposite, which is changing. That's the 40t squared over the side adjacent, which is the 1,000. And then we can simplify this, and it's going to simplify to 1/25 times squared, and this is the tangent of theta. And then what we can do is take the derivative. We want to know the rate of change of theta with respect to time. We have a chain rule problem where theta, which is a function of time, is inside of the tangent function. So we're going to use the chain rule and implicit differentiation. So the derivative of tangent is secant, so we get the secant squared of theta, and then implicitly differentiating, we have to take the derivative of the inside function. So that's just going to be d theta dt, and that's the related rates component of this problem. And over here we get the derivative of 1/25 t squared is just 2/25 times time, and we're being asked to find d theta dt, right? It says find the rate of change of the angle of elevation. So we're really wanting to know what is d theta dt. That's the unknown in this problem. So I'm going to get the d theta dt by itself. And the easiest way to do that is to recognize that the secant function is the reciprocal of the cosine function. So we just need to multiply both sides of the equation by the cosine squared, because cosine squared times secant squared equals 1. Cosine and secant are reciprocals. And multiplying by a reciprocal gives you 1. So we get 2/25 times time times the cosine squared of theta is d theta dt. So now to find d theta dt at the 10-second mark, we're going to need to plug in our our variable values. So we're going to get 2/25 times time, so that's going to be times 10 seconds, times, now we just need to know what the cosine squared of theta is. But at the 10-second mark, we know that the length of this hypotenuse is the 1,000 squared plus 4,000 squared, the square root of that sum, by the Pythagorean theorem. So we know this is 1,000 squared plus 4,000 squared. That's the length of the hypotenuse of the right triangle by the Pythagorean theorem. And the cosine is going to be adjacent over hypotenuse from trigonometry. So it's just going to be, the cosine is going to be the adjacent side over the hypotenuse, which is the 1,000 squared plus the 4,000 squared. And we're squaring the cosine function. It's the cosine squared of the angle theta. So we're squaring this quantity. And when we square things, we're going to get some reducing can happen here. 5 will go in there twice and 5 times, so we get 4/5 times 1,000 squared over, the squaring will cancel the square root, so we're going to have a 1,000 squared plus 4,000 squared sitting in the denominator. And then we want to fuss with this a little bit and see if we can simplify things without having to multiply everything out. So a way to do this is to look at the 1,000 squared plus the 4,000 squared and then recognize that 4,000 is just 4 times 1,000, and we're squaring this, so we're going to get a 1,000 squared plus 4 squared is 16 times 1,000 squared. And the 1,000 squared shows up in both terms and can be factored off. So 1,000 squared times 1 plus 16. So we wind up getting 1,000 squared times 17. So this denominator here can actually be replaced with this simplification to 1,000 squared times 17, and then we see 1,000 squared divided by 1,000 squared is just equal to 1. So this is going to equal 4 times 1 is 4 over 5 times 17 is going to be 50 plus 35. It's going to be 4/85. And this is the rate of change d theta dt, the rate of change of the angle of elevation. I guess I should write the 85 a bit better. And because it's the rate of change of an angle, this angle's swinging through it in the counterclockwise direction, so that's going to be the positive angle measure from trigonometry. So in calculus, we want to work in radians typically. So this is 4/85 radians per, and our time measurement is in seconds.